Hi Year 10, so we're going to look at section 1 in this video. So this video will only look at the multiple choice parts of your end of year exam. So we're going to go through each one in turn. So question 1 says the diagram shows a stone of irregular shape. Which property of the stone can be found by lowering it into a measuring cylinder half filled with water? So you should have chosen C, which is volume. So if you think about it, if we have a measuring cylinder, which obviously has gradient markings up the side, which tells us how much volume of liquid we have, and if it's half filled with water, there will be an original marking, so there will be a volume 1 here. When you merge the object in, it obviously displaces some of the water and causes the water to rise. Okay, and this will give you a new volume reading, volume 2. And then the volume of the stone is just going to be the difference between the two readings. The additional increase in volume of the water has to be because of the volume of the stone. Okay, so volume can be measured using a measuring cylinder. Then in question 2, it says the diagram shows a plastic rod along a ruler. What is the length of the rod? So, first things first, let's look. We've got 0, we've got 10, and we've got 1, 2, 3, 4, 5 increments between. So each one of these is going to be worth 2 centimetres. So obviously this is at the 2 centimetre mark. This is halfway between the 8 and the 10. So this is the 9 centimetre mark. So the length is just going to be 9 minus 2, which gives me 7, which gives me answer C, gives me 7 centimetres. Number 3 is just a memory question. So 3 says, what is the best description of the meaning of the mass of an object? It's not the space occupied by the object, that's obviously the volume of the object. The force that gravity exerts on the object would be weight, not mass. The answer is C, the resistance the resistance of the object to changes in motion. And then D, the option was the closeness of the packing of the molecules in the object. This just tells us the state of the object, doesn't it? It tells us whether we have a solid, a liquid, or a gas. The resistance of the object to changes in motion. So think about Newton's second law, F equals ma. Okay, so if I rearrange this, I get mass is the resultant force divided by its acceleration. So mass is basically telling us how much force is required per acceleration. How much force is required to accelerate the object. Okay, that is basically telling us how hard it is to accelerate it, which is a change in motion. Okay, so resistance, how much it resists, so how much force is required to overcome that resistance, that is what we mean by mass. Number 4, a student uses a stopwatch to time a runner running around a circular track, runs 2 laps twice around. The diagrams show the reading on the stopwatch when the runner starts running, at the end of the first lap, and the end of the second lap. So it should be pretty obvious that the time for the second lap is the time between the first and the second, because they've already ran round once to get to this point, and then they run around again to get to the second point. So we've got 2 minutes and 3 seconds minus 1 minute and 13 seconds. I can convert that to complete seconds if that is helpful. 2 minutes is 120 seconds, so I've got 123 seconds. 1 minute is 60, here I've got 73. Okay, and the difference here is 50 seconds, which gives me A. Okay, let's up to the top. A snail moves along a ruler. It takes 20 seconds to move from Q to R. Okay, what is its average speed from Q to R? So what we need to do is say, well, average speed is the total distance travelled divided by the time taken. Okay. if it ends up at R, which is at the 12 centimetre point, but it started at the 2 centimetre point, the total distance travelled from Q to R is obviously 12 minus 2. And that's in centimetres. And then it tells you that it takes 20 seconds. So our total distance is our 12 minus 2, and the time was 20. And then obviously my distance was in centimetres, my time was in seconds, so that checks out with the units, and that just gives me B. Question 6. 2 distance time graphs and 2 speed time graphs are shown. Which graph represents an object that is at rest? Okay, so in A, as time goes on, the distance travelled increases. That is not an object at rest, which means 0 meters per second or stationary, so we know it is not A. Okay, over time in B, the distance has not changed, so the position of the object stays at this particular value. Okay, so therefore this is okay. Just to check and look at the other graphs so that you're happy with them all. A speed time graph, we can see that the speed is increasing as time goes on, clearly not at rest. And again, although this is a horizontal line, we have a fixed speed value that is not 0, so we are travelling at a constant speed and therefore we're not at rest. Okay, which person is experiencing an acceleration? A driver of a car that is braking to stop at traffic lights. Well, clearly this is changing speed. Okay, now it's slowing down, so it's deceleration, but this just means we have a negative value of acceleration, and so A is correct. Okay, B, a passenger that is stationary, clearly not accelerating. Okay, not changing speed. A shopper in a large store ascending at a uniform rate. This is another way of saying constant speed. Okay, so acceleration is 0 if we're not speeding up or slowing down. Okay, and again, a skydiver falling at constant speed, so A is 0 again here. Question 8. The diagram shows the speed time graph for a train as it travels along a track. For which part of the graph is the train's speed changing at the greatest rate? Okay, so change of speed over time, because remember that rate is looking at how fast it happens, is actually acceleration. So what they're asking for is where is the acceleration greatest? And if you look, this is the y-axis and this is the x-axis. So what we're looking for is the gradient. So the greatest rate, the largest rate, is when the gradient is steepest. Okay, so we've got from P to Q it's horizontal. From P to R, it is accelerating. From R to S, it is also accelerating negatively, but it's still a change in speed. And then S to T, but clearly the steepest part of the graph is this bit. Okay, so that gives us R to S. Okay, so the extension load graph for a spring is shown. The unstretched length of the spring is 17 centimetres in question 9. When an object is suspended from the spring, the length of the spring is 19.2 centimetres. So we firstly need to calculate the extension. How much has the spring extended by? Well, if it's at 19.2 centimetres now, but it's always 17 when there's nothing hung from it, then we know that we've got an extension of 2.2 centimetres. Okay, so what we're going to do is look for 2.2, and then we're going to track across. I would always use a ruler just so you don't mess up with your eyes, because the squares can mess with your eyes a little bit. Okay, and then clearly that was when a load of 3 newtons was hung. Okay, so I go across and down. Okay, so in question 10, it's circular motion. A satellite orbits the Earth in an anti-clockwise direction at a constant speed as shown. When the satellite is in the position shown, in which direction does the resultant force act upon it? In circular motion, the force always acts towards the centre of the circle. Okay, so we look at the circle, we find the centre of the circle that it's travelling in, and the force will always be directed. Okay, so if the satellite were here, the force would be acting in this direction. If the satellite were here, in this direction, and so on. Okay, now that is just one that you need to remember at GCSE level, and hopefully most of you did. Question 11. A car of mass 1,200 kilograms is travelling along a horizontal road. Okay, so you've got multiple forces acting on this car. So we're asked for acceleration, so we are going to use Newton's second law, which is F is ma. We're going to rearrange that and say, okay, well, acceleration is F over m. F here is the resultant force on the object. Okay, and then m is the mass. So, if we've got the engine providing a driving force of 4,000 newtons, but we have friction and air resistance opposing in the other direction of 1,000, then the resultant force is going to be the difference between the two. Okay, so we're going to get 3,000 newtons to the right. Okay. Then we say, okay, well, acceleration, which is F over m, must be 3,000, the resultant force, divided by the mass, which is 1,200. And then when you pop that in your calculator, you are going to get answer C. Okay, question 12. The diagram shows a man holding a sack and barrow stationary. Okay, so stationary means not accelerating, so resultant force must be 0. I know that before I even read anything else. That's the reason they've told me this. He applies a vertical force to the handle. The centre of mass and the weight of the sack and barrow are shown. The wheel acts as a pivot. What is the magnitude of the vertical force exerted by the man? Well, clearly, because we're now told that there is a pivot, we're looking at moments. And again, we know the thing is stationary, so there's no turning effect. We're in equilibrium. Okay, there's no resultant moment. So that means clockwise must equal anti-clockwise if I consider all of the moments. Okay, so let's have a little look. We're trying to find the magnitude of the vertical force exerted by the man. So first things first, a moment is created by a force, and to find the value of the moment, it's the force multiplied by the perpendicular. This is just a shorthand for perpendicular, which means at 90 degrees to distance to the pivot. Okay, so we've got the centre of the mass of the sack and the barrow acting down this way. Okay, the perpendicular distance is one that's at 90 degrees to that line. So I find 90 degrees and I'm going to know that I'm looking at a horizontal distance, and it's the distance from the line of the force to the pivot. So in this case, because the pivot's at the bottom of the wheel, it's that distance there. Okay, now the force exerted by the man is in the opposite direction. It's acting up. Again though, that's vertical, so the perpendicular distance is horizontal. I'm going to want the distance all the way to the pivot point. Okay, so I know then that the distance here is going to be the sum of 45 and 15, and that could have caught you out. Okay, so I've got 60 centimetres is the distance from the force exerted by the man to the pivot, okay? Because we're always going from this pivot point. So, clockwise equals anti-clockwise. Well, clockwise, we've got the weight pulling the wheelbarrow down in a clockwise moment. Anti-clockwise is what we've got by the force exerted by the man. So I can say, clockwise, the weight of the second barrow, which is 200 newtons, multiplied by the perpendicular distance, which is going to be 15 centimetres, must be equal to the force exerted by the man, we'll just call that F, multiplied by its perpendicular distance, which is 60. I can then rearrange this and say that the force is equal to 200 times 15 divided by 60. Okay, and when I do that, I'm going to get 50 newtons. You can check that on your calculator. Okay, and that gets us B. In 13, we have a tennis ball which has a mass of 57 grams. A tennis player hits it with a tennis racket, and the tennis ball has a velocity of 25 meters per second when it hits the racket. The velocity of the tennis ball when it leaves the tennis player's racket is 15 meters per second in the opposite direction from its approaching direction. The average force is 35 newtons. How long is the tennis ball in contact with the tennis racket? Okay. So let's do some rough sketching. So initially we have a tennis ball on its way in, travelling at 25 meters per second. It then collides with the tennis racket and rebounds in the other direction, but this time it's travelling in the opposite direction. So there's a change in momentum. Okay, we know that we've got a total change of velocity of 25 plus 15, not minus with momentum here, because they're in different directions. It has to slow down by 25 meters per second just to become stationary. So we know there's at least a change of 25, but then it needs to gain another 15 to then travel off in the opposite direction. So the total change, so delta V, is 25 plus 15, which is 40 meters per second. That's the total change in velocity. Okay. Now I know that I can find the change in momentum. I'm going to come back up here. mv minus mu is the change in momentum, because this is the final mass times velocity. This is the initial mass times velocity. The difference is the change. Okay. I also know that with impulse, that is equal to force times time. I can pull the m out of the brackets and factorise, and I can say this. Okay, I'm probably going to run out of a little bit of space here, but let's have a little look. I know that what I'm looking for is how long the tennis ball was in contact with the racket. So basically, the racket exerts a force when the tennis ball is in contact over a period of time t in order to change the mass's velocity from v to u, okay, or u to v. So let's rearrange this equation. T is equal to m multiplied by v minus u over f. Okay, I know the mass, I know the total change in velocity is 40 meters per second, so that's this one here, and I know the average force is 35 newtons. The other thing to be wary of, they're doing lots of things in this question to catch you out, is mass needs to be in kilograms for the values to work out. So this is 57 times 10 to the minus 3 kilograms, because we have 1,000 grams in a kilogram. Okay, so what we're going to do is say T is equal to M, which is 57 times 10 to the minus 3 kilograms, multiplied by the change in velocity, which we said was 40, and we're going to divide that by the average force, which was 35, and that is going to give us our value of T. And when you pop that into the calculator, you will get, it'll be rounded, this is a rounded value, but you'll get to 3 decimal places, 0.3 0.065 seconds as your answer. That's a really tricky question that will catch you out in a lot of different ways. So hopefully that makes sense for you now. Come and speak to me if it doesn't. Question 14. A ball of mass 2 kilograms is travelling at a speed of 12 meters per second. It moves towards an object of mass 3 kilograms, which is at rest, which means 0 meters per second. So initially, this doesn't have momentum. Whereas initially the 2 kilogram ball does have momentum. The ball hits the object and sticks to it. Which row gives the total momentum and the speed of both objects immediately after the collision? So, momentum P is mass multiplied by velocity. Because this velocity is initially 0, before the collision, no momentum occurs from here. We know that the momentum of this one is going to be the 12 meters per second multiplied by the 2 kilograms. So we've got 24 kilogram meters per second. And so we sum the two momentum values, 24 and 0, and that tells me the initial momentum, so it's either C or D. And I know that momentum is conserved. Okay, before and after the collision. So now let's look at after the collision has occurred. What we basically have is the square and the circle object now stuck together with a total mass of 2 plus 3 kilograms, which is 5 kilograms. Okay, so remember that momentum P is mass multiplied by velocity. Momentum has to have been conserved before and after, so we've got 24 kilogram meters per second for the momentum is now given to the 5 kilogram total mass, which means it has to have a new velocity. So V is just 24 over 5, and when you do that you will get 4.8, which gives you C. Okay, we're halfway there. The mass of an empty flask is 34 grams. The volume of the liquid added to the flask is 20 centimeters cubed. The total mass of the flask and the liquid is 50 grams. What is the density of the liquid? So, density rho is mass per unit volume. Okay, so mass divided by the volume. We're asked for the density of the liquid, so we need both the mass and the volume of the liquid. If together the flask and the liquid is 50, and the flask by itself is 34, then the liquid mass must be 50 minus 34 grams. Okay, and then we know that the volume is 20. Okay, and when we do that, we're going to get 16 over 20, and when you do 16 over 20, you will get 0.8 grams per centimetre cubed. 16. A 1 kilogram sample of aluminium is stored in a lab. In a different lab in the same town, there is a 1 kilogram sample of iron. Which quantity must these two samples always have in common? Okay, density is mass per unit volume. Although we know that the mass is the same, we're not told what the volume of the aluminium is, so we can't be sure that the density is the same. It should be pretty obvious to you that it might not be the same temperature, weather changes, and by default we've explained that the volume might not be the same. Okay, we might have stretched the aluminium out into different shapes, so therefore weight, which is mass multiplied by gravity, and acceleration due to gravity is just 10, then we know that 1 times 10 is the same for both. It will be the same weight. The energy input to a device is E. Which expression gives the efficiency of the device? So let's just write our general equation for efficiency to start us off. We know that efficiency is the useful energy output divided by the total energy input, and then times 100 to turn it into a percentage. So we've got, here's our device, we've got the total input is E. Okay, the amount of wasted energy is W. So some of the energy goes towards wasted and some of it will be useful. Okay, now useful must be the difference between these two. If I have E to start with, I get rid of W as wasted, then E minus W, total minus wasted, must equal the useful. And that's what I need at the top. Okay, and then obviously it's divided by the total energy in, which is E here. And so that's why we choose C. 18. A stone is released from rest from a high building on Earth. Air resistance is negligible. What is its velocity when it has fallen 5 meters? So if an object falls 5 meters, it loses gravitational potential energy, which means it has gained that value in kinetic energy. There's a transfer, isn't there? Gravitational potential turns to kinetic. So we can say mgh has turned into a half mv squared. All of the gravitational potential energy we had gets converted to kinetic energy. There's a mass on both sides of the equation, so I can just ignore it. If I multiply both sides by 2, I get rid of the half. So I get 2gh equals v squared. I don't want v squared though, I want v because I want the velocity. So if I square root both sides, root 2gh is v. And now all of these things are known because it's just root 2 times g, which is 10, multiplied by the height it went through, which is 5, and that gives me the velocity. Okay, so I've got the square root of 100 is v, which is 10 meters per second, and that gets me answer B. 19, the question is about 4 methods used to produce electrical energy. Which method has a correct description? Okay, so hydroelectric, that's where we've got water falling down through a height, driving a turbine. Yes, it is renewable because the sun continually evaporates water, which then means it reaches the clouds and then it condenses and falls as rain, and so the process continually occurs, and there's no carbon dioxide emitted in that. So A is already the answer. This is correct that coal is not renewable, but it releases carbon dioxide, so that's wrong. Obviously, a wind turbine, also renewable. A nuclear power station, nope, eventually not going to have any more uranium left. So that gives us our reasons for not being B, C or D. 20. An engine produces 240 kilojoules. Remember that kilo means 1,000. So we've got 240 times 1,000 joules in 2 minutes. Again, we convert our time in physics to seconds for equations to work. Okay, power is energy over time. So what I know is I've got 240,000 over 120 seconds. We can cancel these zeros. 24 over 12 is 2. 2 with 3 zeros is 2,000, which is 2 kilowatts, which gives me answer A. 21. The diagram shows a full tank of water. The mass is m. The density is rho. The height is h. Which equation gives the pressure due to water at the bottom of the tank? Well, this is just a memory game because you should know that pressure is rho g h, and it doesn't matter what order you multiply things in. Okay, I can rearrange this and take this h and put it to the back. It will look identical to the one that you should have memorised. So that's a pretty straightforward one there. 22. The diagram shows a solid block resting on a bench. The dimensions are shown. On which labelled surface should the block rest to produce the smallest pressure on the bench? Well, pressure is force divided by area. In this case, it's the weight force of the object that is going to cause pressure. Okay, so I can write weight over area. Now, I can't change this. I can't change the weight. So the only thing I can control is which side and the area of the side is physically in contact. Now, for pressure to be as small as possible, I need my area, the denominator of the fraction, to be as big as possible. So I need the largest possible surface area. So it already rules out Q, because clearly that is just much smaller than P and R. Okay, now P is going to be 80 multiplied by 40. R, though, is going to be 20 times 80. Okay, so the largest area is going to come from P. And we need the area to be very, very big so that the whole thing gets as small as possible in our fraction, which gives us A. Okay, 23. The table gives information about molecules. Which row describes a gas? Again, this is just one that you need to remember. If you've got a gas, there are negligible, so small enough that you can say they don't exist, forces between them. Okay, they're not being held bound to each other, they're free to move. And because of that, they don't stay close together. They have enough energy to move apart. So you just need to choose C. 24. Very small pollen grains are suspended in water. A bright light shines from the side. So you should already be thinking Brownian motion. Okay, when looked at through a microscope, small specks of light are seen to be moving in a random, jerky manner. Okay, so the pollen grains are represented by the dots. We can see them because they're large. The water molecules are not big enough to be seen in this diagram, but obviously each of these pollen grains, if we were to look under the microscope, would be being bombarded by the moving water molecules. So you just need to remember that's what we're talking about when we look at Brownian motion. 25. A block of metal absorbs 200 joules of thermal energy. So that's Q because it's heat, it's thermal energy. The temperature of the block rises from 10 to 20 degrees. So this is a change in temperature of 20 minus 10, which is 10 degrees Celsius. The mass is M, and it asks for the specific heat capacity. So Q equals MC delta T. If I rearrange that, C, which is specific heat capacity, is Q divided by M delta T. Okay, we're told that the thermal energy is 2000. The mass is 2 kilograms, and the change in temperature was 10. So we've got 2000 over 20, which is 200 over 2, which hopefully you can all see means we've got 100 joules per kilogram per degree Celsius. Which statement about boiling and evaporation is correct? Well, again, this is a memory question. Evaporation takes place at the surface of a liquid, but boiling takes place throughout the liquid is the correct answer. Okay. Boiling requires a supply of thermal energy. Yeah, it does. But evaporation does not. Well, that bit's wrong. There still has to be an energy transfer when evaporation happens. And so that's not strictly true. Okay, it's just that on average, some of the particles or the molecules in a liquid already have enough energy in order to escape the liquid. There's still energy involved. When water boils in a kettle, its temperature decreases. That should be pretty obviously wrong. When water evaporates, its temperature increases. Again, wrong. The high energy particles in evaporation leave the liquid. They leave as a gas. that leaves lower energy particles behind, which means the temperature is actually lowered. Okay, 4 more to go. 27. A room is heated by a radiator. The diagrams X and Y show 2 possible circulations of hot air which heat the room. Which diagram and reason explain the heating of the room by convection? Okay, so the radiator is emitting heat. So the air that is close to the radiator is going to start vibrating more as it gains kinetic energy, and it will expand. Okay, so the hot air close to the radiator expands. The mass of the particles hasn't changed, but the space it takes up has. Okay, so the air density decreases. They're not as tightly packed in. So what we have now is hot, less dense air. Cold, more dense air is going to sink to take its place, which pushes the hot air up. Okay, the hot air is not just going to casually horizontally travel along. It's the fact that we've got more dense air up here, where there's loads and loads of air particles much closer together because it's colder, that pushes and takes the place of the hotter air. Okay, so that's why we're choosing X. And that also explains the reason as well. Air density decreases when air is heated. 28. A wave of frequency, which is F, 6,600 Hertz, travels 1,320 meters in 4 seconds. What is the wavelength? Okay. Okay, so we've got V equals F multiplied by lambda. Wave speed is frequency times wavelength. So, to find the speed, we're going to do the distance travelled over time. And that's going to give us V. So that's 1320 over 4. Okay. Lambda, if I rearrange this equation, is V divided by F. So it's going to be my 1320 over 4, which was the speed, over 6,600. And when I do that on my calculator, just to check, yeah, I get 0.05 meters. 29, you've got a diagram showing a wave. What are the amplitude and the wavelength of the wave? So amplitude is maximum displacement. Okay, so it's basically saying how far away from the rest position can a particle get if it's a particular wave. So the rest position is this dotted line. This is where particles are normally. So the furthest we can get is going to be 3 centimetres up, because remember, although the wave is travelling to the right, this is a transverse wave, so the particles are not moving with the wave, they're just oscillating up and down. Okay, so my amplitude is 3. My wavelength is the distance between 2 identical points on the wave. Okay, so we can see here and here are identical points, so therefore we're choosing 3 and 8. Last but not least, number 30, a water wave passes into a region where the wave travels more slowly. As it passes into the slow region, what happens to the frequency and what happens to the wavelength? Okay, so let's say we've got a wave travelling and it's in the faster medium, and then it hits this point, and after this point it's travelling in a new slower medium. Okay, so remember that we can draw wave fronts to represent what's happening here. Okay, so originally our wave might look something like this. Obviously this is not drawn particularly well because it's a quick sketch. But what's happening is these wave fronts are travelling forward, all at a constant speed, and they're reaching the boundary, which is here, and at this point each of these wave fronts slows down, doesn't go quite as quick. The frequency, which is how many waves pass a point per second, has not changed. The same number of waves are still hitting this boundary per second because it hasn't changed how quickly they're entering the medium. Okay, the frequency stays the same. So they're entering at the same rate, but once they're in there, they don't travel as quick. Okay, so instead of a second later, the wavefront reaching over here, which is the same distance as I had before, it might now only reach this point. After another second, it might have reached this point, and then this point. And what has happened is we've squashed our wavefronts up. And remember that wavelength is the distance between wavefronts. Okay, so the wavelength has got smaller, it has decreased. There we go.